You're listening to Professor Megan Workman. Welcome to this brief lesson on tonicity, which describes the relative concentration of two solutions. So during this lesson, you will learn to define solution, solute, and solvent. You will describe the relative concentration of solution in terms of tonicity. And we will end with an evaluation of how IV drip concentrations are designed. Let's first define some key terms. A solution is the resulting mixture of solutes being dissolved into a solvent. To illustrate this with an example, consider instant coffee, which is a solute that you would stir into some hot water. Since the water does the dissolving, it is the solvent, and that produces a delicious solution of coffee. Notice in the cartoon image, though, there are multiple different colors of cartoon blobs being dissolved in this solution, and that's true to life because coffee could contain multiple different types of solutes as well. And while it's common to think of liquid solutions like coffee or ocean water or blood, solutions can also be solids or gases. Metal alloys are solid solutions, and the atmosphere, the air that we're breathing, is a solution of multiple different types of molecules in their gas form. So this makes me wonder, what happens to a cell when it is placed into a solution? The cell membrane will attempt to maintain a healthy cytoplasm, maintaining homeostasis of that internal environment of the cell. But if the cytoplasm is a very different solution from the external environment, bad things could happen to the cell. The diffusion of molecules, both coming into and going out of the cell, might outpace the cell membrane's capability to maintain homeostasis. For instance, it may lose too much water and become dehydrated, or it may take on too many solutes and become poisoned. This has caused the demise of many pet fish. Oh. Improper tank water concentration may kill a fish if water is diffusing into the fish, or perhaps water is diffusing out of a fish, it's becoming dehydrated. But simultaneous to the movement of water, solutes are diffusing in and out of the fish as well. So they may also poison the fish or oppositely deplete it of electrolytes if the solutes are moving out. In order to understand this process, we need to be able to describe the relative concentrations of the fish versus the tank water. And tonicity is the key term that is used to describe these relative concentrations. In the first situation, if the tank water is improper because water is too frequently diffusing into the fish, then the fish might actually puff up, and you can see the golden blob in the upper cartoon. That's representing a fish that is taking in too much water. And notice that the blue arrow pointing into the fish is bigger than the blue arrow pointing out of the fish. These arrows represent the movement of water, and it's true that water is both diffusing in and out of the fish at the same time, but in this situation, the bigger arrow is pointing into the fish, representing the net movement of water in. Like water is moving in more frequently than it's moving out. That's why that arrow is bigger. So in this situation, the fish itself is less watery than the tank water. So water is diffusing in and the fish is puffing up. In this situation, we call the tank water hypotonic relative to the fish. Maybe it's the fish's bloodstream or the cytoplasm in the fish's cells. The tank water is relatively hypotonic to the fish. An example of this could be if you've ever accidentally tried to use distilled water to fill up your fish tank. That will kill your fish pretty quickly because distilled water has no solutes dissolved in it. And so the water is going to diffuse into the fish. Now let's turn our attention to the bottom of the screen. This is the opposite situation in which water is diffusing out of the fish at a faster pace than it's diffusing in. So you can see the blue arrows. The bigger arrow is pointing out of the fish. And this golden ball representing the fish has shrunk. In this situation, the tank water is less watery than the fish. And you'll notice that it has a lot of solutes dissolved in it, more solutes per volume than are contained in the fish's bloodstream. In this case, the fish will dehydrate, losing its own water to the outside environment, and the fish may shrivel up. This situation is called hypertonic, or the fish is placed in a relatively hypertonic solution of tank water. The tank water is hypertonic relative to the fish. An example of this in real life would be if you accidentally tried to put a freshwater fish into a saltwater tank. In order to keep your fish alive, what you want to do is create tank water that is the same concentration as the fish's bloodstream or as the cytoplasm in the fish's cells, while water and solutes are continuously diffusing in and out of the fish. In this situation, you've created tank water that is just right so that water and solutes are coming and going at the same pace. This allows the fish to maintain its concentration, maintain homeostasis. Notice in this cartoon on the bottom that the arrows are the same size. That indicates that water is coming into and out of the fish at the same pace. The fish doesn't notice this movement of water because it's just maintaining its hydration status. It's just right. In this situation, the tank water is described as being isotonic relative to the fish. An example of this would be if you have properly dechlorinated some tap water, and that's the best situation for keeping your freshwater fish alive. Now apply your new knowledge to a clinical healthcare setting. Imagine a patient is being treated for low blood volume, hypovolemia. So they're receiving a saline drip. In this scenario, the IV solution would be designed to be isotonic to blood plasma. And blood is mostly water, 92%, with a little bit of salt, under 0.9%, and other solutes. So in this scenario, the isotonic IV solution would have around 0.9% salt concentration, 92% water. In this scenario, it's healthy because when the red blood cells come into contact with this isotonic solution, they're not going to gain extra water or lose too much water. They're going to be just right. So in the cartoon, you see a red blood cell that is maintaining its shape, which allows it to continue performing its function in the body, which is to deliver oxygen throughout the body. In this scenario, it could be dangerous to instead accidentally give a patient a hypertonic solution, because when it comes in contact with the red blood cells, because it is hypertonic, blood is going to leave the red blood cell into the overly salty concentration of the IV solution that they'd been given. And this causes the cell to shrivel up. In this shriveled state, the cell is not functional. It will not be able to properly deliver oxygen throughout the body, so that can be dangerous. It could also be dangerous in this scenario to accidentally give a patient a hypotonic solution, in which the concentration of the IV solution is more watery, and so it causes water to enter the red blood cell at a fast pace and causing the red blood cell to puff up. In this puffed up state, the red blood cell is also no longer able to perform its function. There are a couple of biology jargon words used to describe the shape of cells in these different scenarios. So a cell that is shriveled up is called crenated. The cell takes on this crenated shape. Oppositely, if a cell puffs up so much that it actually bursts open, same as if you were overfilling a water balloon and it popped, the cell is said to have lysed. Lysis occurs when the cell bursts open, and that kills the cell. Now, let's think of a different scenario. Let's think of a patient who has the appropriate blood volume, but they've just become dehydrated. In this scenario, what type of IV solution would you design? So they don't need more blood volume, they just need more water to enter their cells. I'll give you a moment to think of the answer. Ready? In this scenario, if you want more water to enter their cells because they've been dehydrated, you would treat them with a hypotonic solution. Fun fact. To review what you've learned in this lesson, you learned that a solution is made up of a solute, or perhaps multiple different types of solutes, dissolved in a solvent. And the example we used was coffee, but you could also think about tea. Tea is the solution of tea leaf molecules dissolved in water. You also learned how to describe the relative concentration of different solutions with words hypertonic, isotonic, and hypotonic. And you learned that dangerous crenation or lysis may occur if a cell is placed into a non-isotonic solution.